Hello everyone and welcome to this fourth video that will be part in a series about the assembly language. So today, as we promised in the last video, will be the first video in which we will actually start coding and seeing the general format of an assembly program. So before we actually move into the editing and the writing of code, let's first install the assembler. In fact, we will need an assembler to basically run our code, as we explained in the previous videos. Because after the third video, you should be able to understand it at a little lower level. When we write our assembly code, which is humanly readable, so assembly gets turned by the assembler into machine code, which is binary. And of course, in order to do so, in order to execute the code, we need an assembler. The assembler that we will use is nasm, that for now we will install it using the apt package manager on Ubuntu Linux. But if you have another operating system, another distro based on the Linux kernel, so for example, I don't know, for Arch you can use Pacman, and the process should be almost the same. But for example, if you have for example Windows or macOS, then you can follow some guides on the internet that I will leave in the description, or I'll actually make some videos on how to install it on Windows step by step in the future. So first, of course, make sure that you have updated your apt package manager. And once you have done that, actually run the command to install nasm, and that will be apt-get /y install nasm. And at this point, just wait for the installation process. That should be pretty quick. And at that point, you'll be able to work with nasm, and you will have nasm installed on your computer. So this is the assembler that we will use. But for the text editor, on the other hand, we will use Vim, which, if you do not know, is a terminal-based text editor that usually comes pre-installed. For example, in Ubuntu and many other Linux distros, it is pre-installed. But if you don't have it, but for the text editor, it really doesn't matter. You can use whatever text editor you want, even Nano technically. You could use Nano. You can write assembly code here. Like it really doesn't matter. So you can use whatever text editor if it's your best, or even the text editors I use every day. For example, I don't know if maybe you're more web development oriented and you like the snippets and really use VS Code often, or you could also use VS Code. So with this said, let's now write our first assembly program. But before we do that, I actually prepared a Makefile, and I'll quickly explain what that is. So what is a Makefile? First of all, a Makefile is just we could say a file that allows us to compile stuff more easily. This is a very easy definition of what Makefile is, and I'm sure you've used it at least once if you have been if you program a lot in C or C++, or if you have ever built from source some programs downloaded from GitHub or GitLab. And but in this case we will use it for assembly, because as you can see here, and I copied it here, we could say the copy paste for linking and assembling of our assembly. So for making our assembly an object file first and then turning the object file into binary is pretty long, as you can see. And here I have made a very quick Makefile that you can copy paste actually from here, where all you have to do is to basically change the file name equals with your file name, and in this case let's call it our first program. So this will be the name of our first program, and this is all you have to write. And then by typing make inside the terminal, it will build the file automatically. In this case, it gives an error because, as you can see, there's no file in the current directory at the moment, and so we have to make the file first, of course. Another thing, the file inside which we will put our Makefile instructions needs to be called Makefile with a capital M, and all the other Makefile with a capital M. So with this said, we're now ready to create our first program. So let's create our file, and we called it, as we said earlier, ourFirstProgram.asm. And notice that the extension for assembly file will be asm, so ASM. And now we are in our file and we're editing it. So in an assembly program, let's first say, how do we write comments? So I'm sure you're familiar with maybe, I don't know, whatever language, maybe with Python, with Python you usually write comments with this hashtag symbol as a comment here. In other languages like C, you can write comments with this double slash, and this is actually how you also write comments in JavaScript, for example, and in Java too. And C, in C you can also write multi-line comments like this. So if you have on a multiple line you can comment, you can do this. But in assembly it's a little bit different. In assembly you write comments using this semicolon. And for example, a comment will be comment 1. So whenever you want to comment an assembly instruction, remember that it's not like in C like this, it's a semicolon. And so far we know how to write comments in our assembly program. But we also want to know how to write actual code. So the first thing that we need to know is that for now we just need these 3 main sections, that a assembly program is divided in 3 main sections. And these are an assembly divided in 3 main sections. And these are the BSS section, the data section, and the text section. Actually, .text section, sorry. And what these sections do basically is they have different roles, as you might have imagined. So to declare one of these sections as our code, we need to write section and then .bss. For data it will be section.data, and for text it will be section.text. So let's discuss what each one of these sections does. So the BSS section is responsible for the basically the allocation of space of memory for uninitialized data. And well, what does it mean? It means basically allocating memory for basically variables that have yet to be initialized, that have yet to be assigned a value. On the other hand, in the section data, we will define variables that we have also initialized. So we will define variables and initialize them. On the other hand, in the section text, here we'll go the actual code. So we will put the actual code here. And so these are the 3 main sections that we will use in our programs. And now that we have talked about these sections, let's discuss a little bit the how can we actually define and initialize variables, and how can we allocate space for variables that are not initialized yet. So to do this, we need to talk about a little bit the syntax for doing this, as well as the various data types in assembly. You have 5 types that indicate different data storage sizes, and these are the following. So data types. So the first one is a byte, and that is 8 bits basically. Then the second type is the word, that is 2 bytes or also 16 bits. Then we have a double word, which is 4 bytes, so it's basically 2 words, or also 32 bits. And then we have a quad word, which is basically, you guessed it, 8 bytes, or also 64 bits. And then we have a double quad word, which is 16 bytes or also 128 bits. So these are the data storage sizes for the types of data that we will use in assembly. And now that we know the type of storage sizes that we will use in our assembly programs, let's see how we can initialize variables with a specific data storage size. Let's first cover the section.data. So let's suppose we want to initialize, for example, a variable of a size of a byte, so just 8 bits, and assign to it maybe a number. So how can we do this? Well, we can call our variable, let's call it variable, and then inside the data, so let's actually put a comment here, and the syntax for initializing variables of a specific data size will be d, and then in this quotes I will put a shorthand notation for a storage size, and this is storage size. So to make it more clear, let's look at some examples. So we said we want to define a variable of the size of a byte and assign it to it the number 21. So how can we do this? We set the name of our variable on the left, which is an identifier, and we call it variable. Then we say db, and notice that here, of course, you can put whatever name you want. So MMI, whatever, and 21. You can call it whatever you want, really. But let's call it variable for now. Then we say db. Why? Because as we said above, the general syntax is d and then the size. In this case, the shorthand is db. B stands for byte. And then we set the value, which is 21. Notice that here, in contrast with, for example, C or Java, you do not need to terminate with a semicolon. The semicolon is just for comments. So, for example, here we can comment this line saying we are defining and initializing the variable and assigning to it the value 21. So, and also this variable is of a data storage size of a byte. So in assembly, we also can give inside a variable, we can not only give it a value in decimal, of course, we can also give a value in hexadecimal. So to give a value in hexadecimal, like in most programming languages, let's say, for example, variable 2, we can assign a variable in hexadecimal by starting with 0x. So suppose we want to assign maybe a value of 11, which in hexadecimal is b. Then we just say variable 2 db instead of a byte is equal to 0xb. And so we assigned the value 11, which in hexadecimal is 0xb, to the variable 2. And not only we can assign values inside a numeric values inside a variable in assembly, we can also set them equal to an ASCII character. However, notice that actually there's no difference between an ASCII character and a number between 0 and 2 to the 8 minus 1, because it turns out that ASCII characters are actually mapped as integers. We will see them in the later videos maybe. But for now, let's just know that in assembly, we can actually take my variable 3, assign the value of a byte, and set equal to h. And so, actually, in fact, this is equivalent to going on an ASCII chart online, looking up the number between 0 and 255 that maps to h, and then setting this equal to h. And you can look it up online, but the decimal representation for the ASCII character h in decimal is 72. So if we said, if instead of h, we decided to set it equal to 72, so this 72, this is actually the same, because assembly doesn't care. Actually, there's no distinction between h and 72. Because ASCII characters are stored as just in numbers. But just know that inside the program, to make it more readable, of course, instead of always consulting an ASCII chart and putting the ASCII equivalent of a character, you can just put the character and it will save it as the number that is mapped to that character. Okay, but we also learned that there are other sizes, because of course the byte size only works if we're inserting a number between 0 and 255. But what if we want to insert maybe 341? How can we do that? Well, in this case, we need a bigger variable, and we need a variable of the type, word. So let's define a variable 4. And in this case, again, the syntax is the same, but instead of b, we will put a w that stands for word. And we'll set this variable 4 equal to the value maybe 456. If we try to do this with a byte, it wouldn't have worked, because it would have basically overflowed. Actually, once we will learn about syscalls and input-output with assembly, we will see what happens if you put a number bigger than 255 inside a smaller, basically a variable of a smaller data storage size. But we will see it later. And so for the other data storage sizes, it pretty much works the same. So if we want to define a variable which is actually even bigger, so a double word, then we will say instead of dw, we will say dd, and we will set the value, maybe this huge number here. And then for variable 6, we can also set it equal to bigger numbers. So to a quad word, which is 64 bits, and we can set it equal to an even bigger number, something like this. And we can also set it equal to a double quad word, sorry, like this, and whatever number you want. And also in assembly, like in other programming languages, you can also decide to store floats. So imagine you want to store pi inside a variable, then you can store it using the data storage size you want. Let's store it inside a double word, for example, and then let's maybe store a pi. And this will store the float inside the memory, but it will still be, of course, a sequence of bits. And actually, before we work with floats, I would like to talk about how computers work with floats first. So the mantissa portion and the exponent portion, how they save it in memory. Because remember, to assembly, whether we put an integer or a char or whatever else, he just cares about how it stores it in terms of bits inside the memory. And it's not like high-level languages that also care about how the data that you define functionally work inside your program. It's just bits inside your memory. That's it. And so now that we have seen how assembly data types, data storage sizes work, how we can define an initialized variable inside the data section, there's a question that you might ask, which is a pretty good question, and that is, if you've ever worked with, with algebra systems, with stuff like Mathematica, whatever, you have noticed that you can work with very, very big numbers with over 200 zeros in decimal. And then you might ask, well, how can we work with these big numbers here if the biggest number that we can store, for example, in the 64-bit register is 2 to the 64 minus 1, of course, if it is unsigned. And, well, the answer is big number libraries and big number arithmetic and so on. And it turns out that to work with big numbers, you actually can do it, but you just need to save numbers as arrays of digits. And then on these arrays of digits, you do operations, the classical operations algorithms that you know, but you transform arrays of digits into other arrays of digits by combining them. And for example, for the addition algorithm, most big number libraries use the same as the addition algorithm you learn as a kid. But with multiplication, things start to get a little bit difficult, because if you ever study algorithms, then you know that the classical multiplication has a time complexity of O to the n squared. And so most libraries use the Karatsuba's algorithm instead, or sometimes discrete Fourier transforms calculated with fast Fourier transforms. And actually, the way in which discrete Fourier transforms can be used to compute integer multiplication in a faster way is very interesting. And if you want maybe some videos on this, you can comment it in the comments, and I will surely make a video on it, because I also find it very interesting. So, with this said, we now know how to declare variables inside the section data. We know how to declare simple data types. But now you might ask, how do we define an array? Because in programming languages, having collection of elements, having collection of contiguous memory is very important. Well, it turns out that in assembly we can also do it, and we can define, for example, a variable that we call array1. And now the syntax is the same, so we just say array1. We specify the storage size that we want the elements of this array to be. So let's say that we want quad words, so 64-bit variables. So we say dq, and then we just list the elements with a comma. So for example, 401, 501, 601, 701, and 500, and that's it. This is our array, and this is how you define array in assembly. And you can also define strings. And strings, well, if you're familiar with C, you already know that strings are just arrays of chars. And you define them in the same way. In this case, we work with bytes, because we're working with chars, which are just ASCII characters that are mapped that are represented by 8 bits. And we can write a string, so for example, hello. And this basically is a array of chars. And it is stored in memory as contiguous positions. So with this said, I think we know enough about defining data inside the .data section, even though we haven't yet basically assembled our program, or never run it, or never got any output or gave any input to our program. So the reason why we haven't done this yet, and the reason why we haven't basically explained how to do, for example, a simple hello program in assembly yet, is because I think it is maybe beneficial that we understand a little bit first how assembly deals with data, and actually what syscalls are and how they work, before we actually move on to writing more complex programs in assembly. So with this said, in the next video we will explain, on the other hand, how the BSS section works. So how can we allocate memory